The previous videos demonstrating the use of LTspice have been limited to passive components. Often you will be using active components. The purpose of this video is to give you the tools you need to create and simulate an operational amplifier circuit in LTspice. For simplicity, we'll make a standard inverting amplifier. Let's start by building the schematic. Open LTspice and go to File and New Schematic. To begin, let's find the operational amplifier component inside of LTspice. To do this, we need to use the component function that can be accessed from the Edit menu, the component icon, or by pressing the letter P. When we first open the component dialog, the top-level menu has a directory for operational amplifiers called op-amps. Double-clicking onto this directory will produce a list of available operational amplifiers. For this demonstration, I will use the op27. To add this part, we can either search or click into the op-amp directory and navigate to the desired part. There are other common operational amplifiers that are available, but not all come in the default libraries of LTspice. I will show how to add an operational amplifier like the UA741 to the LTspice library in a separate video. Since there are several components we're going to add to the schematic, I'm going to place the part in the center of the diagram. Next, I would like to make sure the operational amplifier has DC power. To add a voltage source, simply press V. The operational amplifier has a bipolar supply, so two DC supplies will be needed. I will also place a ground associated with the power supplies in between them. Typing W will enter wiring mode. I can then make the appropriate connections for this portion of the circuit. Wiring starts when I click on an unconnected terminal. In order to create corners, a single left click creates a change in direction. It is necessary to change the value of these sources to an appropriate value. In this case, I will choose 10 volts. Since the ground is the 0 point between the sources, this will produce bipolar supplies. With that complete, the signal portion of the circuit can be constructed. I'll start by placing 3 resistors. Pressing R allows me to place an input resistor. If it is necessary to rotate a part while in place part mode, Ctrl R will rotate the part. Left-clicking places the resistor. Remember to place the parts so neither the parts nor the text associated with the parts overlap. Since I'm drawing a relatively arbitrary circuit, I'm going to choose a gain value of 10 volts per volt. To do this, I will make the input resistor 1 kiloohm and the feedback resistor 10 kiloohms. The value of the load resistor is relatively arbitrary. I will choose 330 ohms to create a unique value. To change the values of the resistors, right-click over the resistor and enter the appropriate value in the dialog box. It may be necessary to zoom out on the schematic diagram while constructing it. The View menu can be used to zoom out. Shift-Z will also perform this function. Pressing the space bar will fit the circuit into view. Since we still have components to add to the circuit, I will zoom back so there is more room around the circuit. We need an input voltage source. The most common simulations done with an op-amp circuit are a transient analysis or an AC sweep. To do either of these, we need a general voltage source. Type V to add a voltage source and place it left of the rest of the components. Let's set up the source for an AC simulation to begin with. Right-click on the new voltage source. Select the Advance button. In the small signal AC analysis area, enter 1 volt for the magnitude and 0 degrees for the phase shift and click OK. We can then place the grounds. Typing G brings in the ground. We need to place 1 below the signal source, 1 for the non-inverting input, and 1 below the load. All of the ground symbols represent the same electrical point. Using multiple ground symbols in the same schematic tends to make a cleaner looking diagram. The next step is to wire the circuit. Selecting the wiring tool or typing the letter W can begin the wiring process. Remember, single click to start a wire, click to change directions, and click once more to terminate the wire. Be careful not to click on wires that cross unless they are to be connected. Once all the connections have been made, we can then move on to the simulation. To set up the simulation, click on the Simulate menu and select Configure Analysis, or click on the Configure Analysis icon and the Configure Analysis dialog opens. We are starting with an AC analysis. The handout says to create a decade sweep that goes from 1 Hz to 10 MHz with 10 points per decade. Remember that in Spice, MEG is necessary to get mega. Clicking OK will allow us to place the .AC directive in the schematic. Clicking on the green Run button will result in the program performing an AC analysis. To see the results of the output, move the cursor over the output node of the op amp until the voltage probe icon appears and click. The decibel magnitude and phase of the output relative to the input signal will appear on the graph. The default trace width does not necessarily appear well on screens. To change the trace width, right-click on the graph window and select Waveform Settings. The data trace width can then be increased to improve trace visibility. I will select 5. The text on the axes may also be too small, or a particular font may be undesired. These can be changed in the same dialog. Most IEEE documents are in Times New Roman, so I will select that and increase the font size to 16. These can be adjusted as necessary. We see that at low frequency, because we selected a gain of 10 volts per volt, the gain is 20 decibels. As we look at higher frequencies, that gain falls off, and the phase line is less constant. But we see at low frequencies, the phase shift of our inverting amplifier is 180 degrees, as we would expect. As the simulation goes to higher frequencies, the limitations of the operational amplifier cause the magnitude and phase to change. Another type of simulation that might be useful would be a transient analysis. That is a time domain analysis like an oscilloscope would display. To do this type of analysis, we only need to make a few changes. The first is to edit the source from an AC source to a sinusoidal source. Right-click on the signal source and select Sine under Functions. We can then change the amplitude. In this case, I'll choose 10 millivolts, and I will set the frequency at 10 kilohertz. The other parameters are not relevant to a basic transient analysis, so they can be left blank. Once I've clicked OK, the sine characteristics will appear near the voltage source. If the text overlaps something, typing M will put the cursor in move mode, and then I can click and drag the text to a new location. Escape ends move mode. Typing A will open the Configure Analysis dialog. This time we are doing a transient analysis. Since the source is set to 10 kHz, the period of the input is 100 microseconds. I would like to see a couple of complete waveforms, so I will set the stop time to 200 microseconds by typing 200U. This is a simple circuit, so we do not need to change the time to start saving data. I like to keep the maximum time step at least 100 times smaller than the period of the wave in order to get a nice smooth plot, so I will set that to 1 microsecond. Making the time step too large will result in a jagged graph. Making the time step too small will greatly increase the time it takes for the program to simulate the circuit. Clicking OK will allow me to place the .tran directive. Notice that the .ac directive changes color, indicating that the .ac directive is not active. Clicking the Run button will cause the simulation to run. After the simulation is complete, I will click on the input node of the op-amp circuit so that both the input and output appear on the graph. It is then easy to see that the output is an inverted sinusoid relative to the input signal and is 10 times larger. Just as a note, if we need the simulation or the schematic for a report, right-clicking on the waveform brings up the option Copy Image to Clipboard. Once selected, the waveform can then be pasted into a document. For the schematic, right-click and then go to the View menu. Then Copy Image to Clipboard can be selected. The schematic can then be pasted into a document. That's all I have for you today. Go out and make it a great one.